Hello, my name is Diego Borne, and today I'll be presenting to you a paper titled Weakly Supervised Thoracic Disease Localization via Disease Masks. This paper was in the Neurocomputing Journal and was performed by a few researchers from the University of Korea. So, introduction, why are we here? Computer-aided diagnosis tools are already well established. We have the ability to take an input X-ray, chest X-ray, and output what diseases might be present. So we've sort of achieved classification. But the next step for these tools is accurate disease localization. So we want these tools to be more useful to radiologists and be able to provide a second impression on difficult chest X-rays, when we can't exactly determine where diseases are located. The issue with this problem is that there is a limited amount of high quality labeled data, so we can't take the typical deep learning approach, and we need to take a weakly supervised approach because it's expensive and time consuming to produce all this data. And so we're looking for a way around that. We're looking to have a weakly supervised model. The literature review, several references in pieces of literature are mentioned. Class activation maps and spatial attention are prevalent in quite a few of these references because localization is the name of the game. What we're attempting to do with these class activation maps and these attention methods is extract the discriminative features from our classifiers and then focus our models based on these features. We see a pattern of two-step approaches just because we have to extract these class activation maps in the first place. This is typically the first step, and then the second step is performing some sort of operation on the activation maps or on the input images given the information from the class activation maps. Dropping is used in a few approaches, so random grid-based dropping was used in a few references, and additionally dropping class activation maps from input images like areas of high discriminative features would also be dropped. It's important to note this publication, which publishes a chest X-ray dataset, which was used universally in all the references mentioned, as well as this paper. So this dataset is used in testing, validation, and training for this paper. Additionally, another reference proposed an alignment module, and this paper additionally proposes and utilizes an alignment module, and both of these models were able to perform quite well. So our alignment module is an attempt at reducing input noise and variation. It utilizes perceptual and Euclidean loss, and it trains to an anchor image. So we're attempting to train a model which can transform our input images and reduce variation in hopes that our final feature extractor might produce better results. Disease masks, the main feature of this paper. We're utilizing class activation maps from a pre-trained network to produce disease, occurrence distributions. And so then we can retrain our feature extractor. We're giving our feature extractor spatial attention here, and we see we have here the 8 disease masks for 8 diseases, and in the same way that a radiologist would look at a specific location for specific diseases, provided a chest X-ray, we're allowing our model to look in specific places more carefully with these disease masks. Additionally, a weighted cross-entropy loss is proposed and utilized, and it accounts for the data imbalance in medical data sets. So we don't want a skewed classifier, so we weight our binary cross-entropy loss given the frequency of sort of positives and negatives, and we're able to avoid this skewed results of the data set. Here we're looking at localization performance based on intersection of union as our metric. At the bottom here, in each sort of division, we have our current model. Previous versions of the model and rivaling models are included above. The bold values are our best performance, and so we see that our model is performing the best on average. It has some of the highest scores and some of the most bold numbers, so it's performing better than most other models. It's not blowing the whole problem out of the water, but it's definitely a step in the right direction. So we're seeing this sort of incremental improvement. It's definitely not the final answer for this problem, but we're making good improvements, and it's still a very interesting and useful architecture. Here we see further results. We see classification performance here, and all the way on the right we can see that our model has some of the highest performance in quite a few different areas. Additionally, on table 4, we're seeing how each of these modules that we actually contributed are making a difference and are improving the performance of our model. So what did we talk about today? We talked about an alignment module, which helps us to standardize our input images, and we talked about disease masks, which are able to give a feature extractor spatial attention via the class activation maps from a pre-trained classifier. So we're providing spatial attention and then using a sort of tailored loss function, which avoids providing a skewed classifier from our data set because of data imbalances. And from this model, we're able to produce better localization. Again, this isn't the final answer for this problem, but definitely a step in the right direction. And it's the most interesting and useful part of this is the architecture, in that the alignment module, the loss function, and the disease masks are used, and they're used to improve performance on this problem. Thank you so much for watching.